So we are going to talk today about the sample transform fault system that lies in the Equatorial Atlantic, and focusing mostly on the geophysical studies that have been done there, that we are still doing, still publishing these results. And but actually the work that's been done there is the fruit of the collaboration of a larger team, including petrologists, geochemists, and seismologists and a lot of people. And we hopefully in the next 2 years, the papers summarizing the results will come out, will be published and come out. So without delay, let's start by reminding what, okay, doesn't work. Why it doesn't work? Just a minute. Okay, I find it's fine. So without delay, let's talk about what a transform fault is. There are just a few basic concepts that I like to remind every time I give a talk about the sample. So transform faults are lithospheric features, and they are plate boundaries, as there's a concept that was first thought about by Wilson, published in '65 in the very early days of plate tectonics. And do you see the mouse when it moves? Hopefully. Okay, so transform faults are strike-slip plate boundaries, and which means that displacement is located mainly along the fault, and it's a conservative, or supposed to be a conservative plate boundary which implies that there is no creation or destruction of the lithosphere. And transform faults can be either continental or oceanic or transitional between both. And Wilson recognized several kinds of transform faults if they connect divergent plate boundaries, convergent plate boundaries, or a mix between divergent and convergent plate boundaries. We're going to talk about the first case, which is a transform fault that is connecting two ridge segments to divergent plate boundaries, and which are by far the majority of the case of transforms. Okay, so as they are plate boundaries, they can deform due to changes in plate motion. So according to the change in plate motion and to the sense of the offset of the transform fault, we may have transtension and transpression happening along these plate boundaries. So if we have a counterclockwise movement and left stepping offset, we are going to induce extension in the transform domain. And on the same kind of offset, if we have a clockwise, we may induce compression. So these are two examples of a counterclockwise change in plate spreading with two opposite sense of the offsets, the Siqueiros and the Clipperton. And in one, we induced extension with creation of small pull-apart basins that evolved in small intra-transform segments, and flexural ridges and hooked features. So this is very typical of transtension along fast spreading ridges. And here we have the Clipperton, where the same change induced compression, and we have a very typical feature, which is a large compressive ridge that formed inside the transform domain. So according to the change in plate motion, to the offset, to the sense of the offset, we may have very different features that are going to evolve inside the transform domain following a change in plate motion. So, okay. So there are several parameters that may also play a major role in the way this deformation forms. We have the amplitude, of course, of the change in plate motion, the ages of the lithosphere. I mean, a young lithosphere is not going to react the same way as an older lithosphere, and so therefore faster rates transforms are going to deform differently from slow spreading rates transforms. So it depends also, of course, on the length of the offset and of the contrast of the ages of lithosphere that are involved in the change. Here are an example of the Atlantic, where you can see different transform from the Vima transform to the Romanche transform with very different lengths of offsets. So it's the same spreading rate. So now you have the Vima, which is 300, Strakov 100, and doldrums and St. Paul, which are roughly the same, about 600, and a very large Romanche here. And if you compare the reaction of the Vima, which is 300 kilometers, and the Strakov, which is about 100 kilometers, that underwent roughly the same change in plate spreading with about 10 million years ago, that induced the formation of a flexural ridge in Vima. We see that on Strakov we don't see any flexural ridge. So this means that the ages of the lithosphere that are involved in the process and the length of the offset are important factors on how the transforms evolve. So one of the most spectacular things that happen when we have changes in plate motions involve large offsets are multi-segmented features, multi-fold transform, very complex features. This is evolved from a concept that was first developed by Menard and Atwater in 69, when they proposed that extension along transform faults might induce volcanism inside the transform, and so they developed the concept of leaky transforms. These are very commonly observed on fast rates along the East Pacific rise. One classical example is the Quebrada Gofar system, which was first studied by Searle, and he proposed that actually it was a response to a change in plate motion that created a series of small intra-transform segments in Gofar and in Quebrada and in the Discovery transform fault systems. So if you have extension and a large offset, you might expect to have this kind of feature, as for example, here in the Molokai fracture zone, a transform and fracture zone system was proposed by Searle in 1993. So these features are commonly observed along the axis of the East Pacific rise nowadays, but they are far less common along slow spreading ridges like the Mid-Atlantic Ridge. The two better known examples that we have are the doldrums and the St. Paul systems. The doldrums was studied by the Sokolev and colleagues, and there is a published paper in 2020 that shows the bathymetry of these features. As I said, that the total Mid-Atlantic Ridge offset between the two main axes of the ridge in the north and in the south of the system, it's about 600 kilometers. And this very large offset is actually accommodated by the offsets of 5 transform faults, with very variable offsets, and range from about 180 to 40 kilometers. That separate 4 intra-transform ridge segments that have lengths ranging from 55 to 16 kilometers. We know there is a large amount of peridotite that was dredged along the transform valleys, and there is also evidence of detachment faults that were observed by our colleagues in the intra-transform ridge segment, which suggests a very tectonic dominated spreading for these segments. So now if you look at St. Paul, in order to have the second example of these multi-segmented features, the total offset length of the St. Paul between the north of the system and south of the system is about the same, 580 kilometers, 600 kilometers. And we have this offset being accommodated by 4 transform faults that separate 3 intra-transform segments. The St. Paul is part of the so-called Equatorial Atlantic cold spots, which is characterized by very deep axial depths that was reported first by Schilling in a paper in 1995, and also the basalts that were dredged along these ridge segments show very low melt rates and therefore yielding low average crustal thicknesses and for the basalts, for the actual basalts. So Schilling and Bonacci, and they developed the concept that the Equatorial Atlantic would be an area where the mantle would not favor high amount of melt, and therefore would be a cold mantle spot. And the transition would be around the St. Paul system, between the northern part, a northern mantle that would be more fertile and melt more, and the southern mantle that would be lower temperature or a different composition that would be yield lower melt degrees. So St. Paul also shows a very unique features, which are the St. Peter and St. Paul islets. They were first studied by Charles Darwin when he stopped there during his tour of the world, and they intrigued very much Darwin, and he was the first one to say that these rocks have a completely different origin from the other islands in the Atlantic, the other volcanic islands that he has been studying. And so actually they are formed by mantle rocks. And so there are several studies that show that these rocks are formed by peridotite, highly deformed peridotite, different degrees of serpentinization. Here there is a map that was drawn by one of my colleagues, Thomas Campos, showing the distribution of these peridotites on the islets of St. Paul. So the question is, which kind of process would be responsible for the uplift of such a large slice of mantle rock? Because the islets, it's themselves, they are part of a large submarine ridge. And considering the depth, it's about 4,000 meters, and the mantle should be at, let's say, 5 to 6 kilometers below the seafloor, we would have an uplift of about 10 kilometers. So it's huge. And one of the questions that we wanted to answer when we went there to study this area was, what was the process that could be responsible for this uplift? There are other studies on the intra-transform ridge segments. One is published by Ekinian in 2000 that showed that there was also a large amount of peridotites along these intra-transform ridge segments. He studied in detail the southernmost intra-transform ridge segments in the actual area, and he showed that both flanks of the ridge were formed exposed, actually gabbros and a lot of peridotites. And so he came with a model saying that these intra-transform ridge segments was magmatically starved, and he generalized it for the other ridge segments, saying that we would have a very low melt degrees, and therefore we would expose mantle rocks on both sides of the ridge flanks. So we have several questions that we are going to deal in this talk. First, which are the spreading process inside at the inter-transform ridge segments? Which are the dimensions of these mantle ridge and the connection with the transform faults, and also what is the evolution of the transform system through time. So mainly I'm going to present you the results from the analysis of the bathymetry, seismic, and gravity data, and just a little bit of geochemistry, but not very much, because this is not what I am doing. I mean, this is going to be published and dealt with by other colleagues. So we are going to talk about the evolution of the system since its opening, then the morphology and cross-substructure of the transform faults, the origin of the St. Peter St. Paul islets, then the morphology of the inter-transform segments, and then the connection of the mantle composition and transform offsets and the implication that it has for the spreading process themselves. Okay, so zoom in detail of the St. Paul, we see that it is formed by 4 transform faults. The length of the offset diminishes towards the south from 300 up to 40 kilometers, and they offset 3 intra-transform ridge segments, which are quite small, with lengths around 30 kilometers, and the shortest one being the southernmost one, which is about 20 kilometers. Now, if you look at the evolution in time of the system, what we did is that we calculated the basement topography by subtracting the sediment thickness in the area, and we could map the discontinuities up to the end of a survey zone, which is about 40, 48, 45 million years. Now it's a little bit difficult to work in the equatorial area because we are close to the magnetic equator, so we don't have actually we don't have any magnetic age constraints for the system. So what we did in order to study the time evolution is that we took the present day position of the ridge axis and we reconstructed it past in time, the past, using rotation poles. So we choose those of Shaw and Kendall that are published in 1990 because they fit well the VIMA ages. So we choose these ones. And we mapped the discontinuities. So the first thing that we can see is that some transform limits, as for example, the fracture zone that is connected to the southern transform, actually is very stable in time. It's something that remained there since the opening of the system. And the other discontinuities, for example, the one between the south segment and the central segment, actually become rather unstable in time. So they show more instability. So I have to go back one. Yeah, here. So if we take the center of the segments and reconstruct the position back in time using the rotation poles, we can have some constraints on the age of the lithosphere of these segments and when they form. So to make it simple, the idea that we have is that the south segment was one of the earliest, if not the earliest, to form, and it has been quite stable, but passed through some periods of instability in the past. The youngest segment, I mean, the last to be formed, was the north segment, which started to form between 26 and 20 million years ago, and the central segment showed actually a much more complex evolution history with a lot of interplay between the central segment and south segment in the early times of the system. So one of the conclusions that the lithospheric ages of the segment they're not the same. The oldest segments lie in the south, and then the youngest one is in the north. So this means that we had a progressive opening of the system. And the northern part it's quite younger and more stable, and very quickly it evolved on transform faults. The discontinuities evolved on transform faults. And then the south, which is an older part of the system, actually there was some instability, especially between 33 and 20 million years. And from 20 million years ago to the present time, we reached the kind of stability, and the transform faults were stabilized and better defined, and then we had the spreading segments that we see today. So this probably is related to the cease of the stopping of the transtension inside the system, or a considerable reduction of transtension inside the system, which resulted in the stabilization of the system. So if we go now for the structure of the sand pole, to do that, we used gravity, and we computed the classical residual Mantle-Bouguer anomaly, and we inverted to get crustal thicknesses. And now we are going to detail the transforms and then the intra-transform segments. So we are starting with the simple transforms, which are transform A, C, and D, and leave the more complex one, which is transform A, to the end. Transform B, it's about 140 kilometers long, with an average depth of 4,200 meters and an average crust of 6 kilometers, which is very close to a near normal oceanic crustal thickness. We have some complexities in the fault, with some restraining bands and releasing bands, and with small pressure ridges near the restraining bands, and the kind of extensional basing on the releasing band here. And this is also associated with some crustal thickening and thinning in these two features. Transform C is slightly smaller. It's also a little bit complex. We had a kind of restraining band here, which is also associated with some crustal thickening, and it's also associated with a small pressure ridge. It's slightly deeper and has a slightly thinner crust. Transform D, it's the shortest one, and it's also the deepest one. It's about 4,500 meters deep, and also associated with a roughly 4 kilometers thick crust, so the thinnest crust of all the transform faults, and has a very complex fault line with some double lines that could be mapped along the inside the transform valley. So now transform A is by far the more complex one, because it is related to a large topographic ridge, which is the Atoba ridge, and the summit of this ridge form the islets of St. Peter and St. Paul that we talked previously about. And we have two more normal portions of this transform on the east part and on the western part. So the transform itself is about 300 kilometers long, and Atoba is about 200 kilometers, so it leaves us about 100 kilometers of near normal transform fault. It's shallower than the other one. It's about 3,900 meters deep, and the average depth of Atoba it's much less, closer to 3,000. And the transform A is associated with a thicker crust, even if we remove Atoba from the system, and Atoba itself it's very thick in average. What is also important to know is that in Atoba, most of the samples actually are formed by peridocites, and the serpentinized peridocites, highly deformed. We have some basalts, especially on this area here on the northern part of the ridge, but mostly they are mantle. So actually what you see here in what is supposed to be thickened crust, actually is more probably serpentinized and altered mantle than magmatic crust itself. So if we compare now the different transform faults of the system, you can see that we have a relatively good correlation between depth, which is shown here in the blue. This is the average depth, this is the maximum depth, this is the average, and the crustal thickness, which is shown by the red dots. It means that the shortest, the deepest transform has also the thinnest crust, and it's also the shortest transform that have the thinnest crust. If we compare, of course, the transform A, if you consider the full length, which corresponds to the age contrast, it fits also this trend. I mean, it's longer, has a kind of thicker crust, and it's shallower. And if you consider Atoba, which is here, it's something that stands completely out. It's very anomalous, of course, concerning the pattern of normal transform faults. Now, if you put the transform faults in St. Paul in the global study that was published very recently by Ren and colleagues, where he considered different transform systems around the world, and if you compare the depth of the transform and the length of the offsets, the three shortest transform faults of St. Paul lie in the group of the smallest offset, and the larger one would be around here. What we can see is that in our case, in the case of St. Paul, the larger offsets are not, which correspond to larger age contrasts, as not necessarily the deepest ones. Actually, they are shallower than the smaller ones. So it is a little bit different from the conclusions they have in their study, and we will see why St. Paul falls a little bit out of it. Now, if you compare St. Paul and doldrums, which are roughly equivalent systems, we also see that St. Paul, which is shown here in red, are deeper than the doldrums transform, if you consider an equivalent offset. So we have St. Paul that falls a little bit out of the conclusions of global studies, and it's also a little bit different because it's deeper than what was observed in a similar system of the Atlantic, which is doldrums. We will go back to this point a little bit later. So now if you go to Atoba, Atoba, as I said, is something that is very unusual. It's very particular. It's a unique feature in the world. By the way, Atoba is the name of a marine bird that nests in these islets shown there. And the Atoba Ridge is part of a very complex shear zone that sits along transform A, which is characterized by multiple faults. It's a segmented fault, and there are evidence of transpressive features along this shear zone, and the strongest evidence is the Atoba itself, as you can see. We also, during our cruise, we mapped some thrust faults in the south flanks of Atoba, and I'm going to go back to this sooner. But let's now look at the more normal parts of the transform fault, which are, as I said, on the west and on the east. Now, on the west, we see also some multi-segmented features with some transpressive pull-up, push-up ridges here. So there is some compression still going on there. And on the contrary, on this part of the system, we have a very deep basin, almost devoid of sediments. And this is probably something that it's maybe undergoing some extension, or it's just the normal fault itself. The central part is the Atoba. And the Atoba is formed near a very large restraining band of the transform fault. And it's, as I said, associated with a thick low velocity layer, because I don't like to call it crust, because the rocks that we sample there are mantle. So this is probably altered mantle, but very thick, except for the center where we see the islets, where we see a more thinner crust. And this is probably due to some rotation, that it's uplifting a plug-in mantle, that it's forming the rocks itself. So if we look at the thrust faults that we're seeing in the south, a seismic line that we have there shows a kind of positive flower structure, which is actually forming the Mid-Atlantic Ridge, the peridotite Mid-Atlantic Ridge in the center. And there is also additional evidence for compression along the system, because there are a few focal mechanisms that were studied by Cecily Wolf and colleagues, and that show that we have some compression there, but the location of these, it's not very good, but we postulate that they are actually located along these thrust faults in the southern part of Atoba. And also we have measurements of uplift, and we know that we have a continuous uplift of the rocks that is still active today. So there is compression, and that creates this uplift. And if you look at the structure of Atoba and compare with analog laboratory models of transpressive features, you see that the shape of Atoba and the distribution of the strike and slip faults and of the thrust faults is very similar from the results of these laboratory experiments, as the one here from Maclay and Bonora, and we see that we have the same structural pattern that we observe in Atoba, and also a cross profile along one of the points of the ridge. So these positive flower structures, which are very, very similar to what we see in the seismic. So Atoba is a transpressive feature, and the origin of the ridge itself is actually linked with a small change in plate motion in about 10 million years ago that created on the Vima the large flexural ridge. So here in this area you also had a flexural ridge that sits on the northern lithosphere. It's the blue ridge here. But what is different from Vima is that we had a progression, I mean a propagation of the northern ridge segment into the transform domain, and these induced actually the breakup and the shift of the transform boundary that tried to adapt to that mechanism, and these created the small offsets and the small restraining bands along this fault. And it's along these restraining bands that we have the major compressive force, and then we form the compressive Atoba ridge. So the compression is linked to the southward elongation of the North Mars segment, while the segment here remained relatively stable. So the question is why? Why we had this particular functioning in this part of the system? So what we do is that we have a very robust Mars segment in the north, and the volcanism that is shown by the volcanism and very linear abyssal hills in absence of core complex here, which is related to an abundant melt supply. And we believe that this, do you still have me? Okay, sorry. We believe that this could be linked to the presence of thermo-mechanical anomaly in the north, which is related to probably to the Sierra Leone plume. And this is something that we see in the chemical composition of the rocks. I already showed the one published by Schilling, showing that we have two distinct mantle domains, one in the north, which is specially located in the segment north of St. Paul, which is fertile, and another one in the south that is less fertile. And the transition is around the St. Paul. And it is the fact that we have this very enriched mantle and very fertile mantle here that helps propagating the segment of the Mid-Atlantic Ridge to the south, inducing this deformation that resulted in the Atoba Ridge. So a kind of mantle boundary here. So what does this mean by to the spreading inside the St. Paul system? First, let's look at the chemical composition of the intra-transform ridge segments and the north and south Mars segments. In green, we have the south domain, and in blue, we have the north domain. And what you can see is that the intra-transform segments north actually has the same kind of composition as the north Mars domain. So this segment is actually very similar in terms of fertility to the north Mars segment that's propagating south and that is so vigorous in propagating south, while the south segment and the central segment belong to another province, which is actually the southern province of the mantle, the southern mantle domain, which is less enriched and have lower melt degrees. And what we see is that the structure of the segments, they show actually this change in mental nature. Oh, okay. So the intra-transform segment north, accordingly, is actually a quite volcanic segment. We see here these Abyssal Hills here. It's a typical small Mars segment with this symmetry in the residual mantle bouquet, which is actually translates in terms of crustal structure. And the samples here show gabbro, serpentinized peridotite in the north, but mostly they return basalts. And what we do have here is that we have a core complex on the west flank and abyssal hills, volcanic abyssal hills on the east flank. So in the south we have the opposite. So it's a very classical volcanic Mid-Atlantic Ridge segment with less magmatic flank on the west, dominated by detachment faults, and abyssal hills on the east. Pardon. Do you still see my thing? Because I think I lost it. So the central segment actually is very different from the north segment, and we see that we have a symmetrical structure in terms of crust, and in terms of morphology, it's very symmetrical in the north and asymmetrical in the south. And a zoom in the feature shows that we have these oblique ridges that are actually associated with peridotite. They are peridotite ridges, and we have a kind of OCC on the west flank that it's associated with gabbro. And all the features of this central segment are actually associated with thin crust. Now, the south segment, it's very particular. It's very asymmetric. I'm not going into detail because there is a paper that's going to be published soon about the evolution of this segment. But it's the one that is associated with thin crust. And we have samples that return gabbro and peridotites. And we have a very asymmetric morphology, which is actually, we interpret as being formed by fragments of detachment surface that are on the west flank, and terminations and the tips of OCCs that are located on the east flank. And this particular geometry is actually related to a series of ridge jumps that broke the detachment surfaces in two fragments, leaving part the terminations on one flank of the ridge and the rest of the OCC on the other flank of the ridge. So this means that we had a long-term functioning in the segment that is related to detachment. It's so very asymmetrical. And one of the main means of recovering this asymmetry is through small ridge jumps that are going to rupture the detachment surface, leaving fragments in both flanks of the ridge. So now if we compare the three segments among themselves, we see that we have south segment, north segment, and central segment. And if we consider in terms of length, the shortest segment is deeper and has thinner crust than the longer northern one. However, the central segment does not fit this trend because it's the longest, but it's the deepest. It's one of the deepest, and it's also associated with thin crust. And if we look at the chemical composition, we see that the north segment actually has a composition that, as I said, it's different from the south and the central one, and it's more linked to what's happening in the north of the system, while the central and south segment have a similar composition and belong to this low melt degree depleted mantle in the south. So there is something else that it's contributing to the differences that we see between the central segment and south segment and the north segment. And we postulate that this is actually linked to the effect of cold edge effects of the transform faults. In the north, we have for inter-transform segment, the north inter-transform segment here, we have a strong cold edge effect because the transforms there are very long. So this effect is very important for the north inter-transform segment, and it's a little bit smaller for the central inter-transform segment, and it's very small for the south ones because the length of the offset is very small. However, why do we see a magmatic segment in the north? It's probably because this effect is balanced by the fact that we have a more fertile mantle feeding this segment, and therefore inducing a more magmatic spreading. In the south segment, the cold edge effect is not very strong, but it's balanced by the fact that we have a less fertile mantle. So we have a spreading that is dominated by tectonics, but we still have a lot of gabbro there. We still have core complexes, and we have something that shows that there is still some magmatism going on there. However, in the central segment, which appears to have a really very magmatic spreading, where we do see these peridotite ridges, symmetrical peridotite ridges on both flanks of the ridge, and we don't see that much gabbro. We think that what is happening there is that we have accumulated effect of the transform offsets that are still quite large and induce a cooling of the segment, and the fact that we have less fertile mantle and that it's feeding this ridge segment. So what we learned from the system First is that in terms of transform faults, there is a good correlation between depth and crustal thickness, and the deep valleys match more or less thin crust. However, the larger age of set are not the deepest valleys. But in St. Paul, this is probably related to this transition that we have inside the system, and it's affecting mostly transform C and D, and also a little bit of transform B. And so these induces the deepest valleys associated with these transforms that are also linked to lower melt supply and lower melt production. In terms of spreading, the cooling edge effect that is expected from the large axial offsets in some of these inter-transform ridge segments is balanced by the fertility of the underlying mantle. And this allows a near normal spreading for the intra-transform segment north. The actual melt supply will diminish for the center and the south, but still there is some melt available in the south. So this is probably because the cooling edge effect is not as strong for this segment. And in the central segment, which is the most melt deprived, we have accumulated influence of the large offsets and of depleted mantle. So we have the peridotite hills on both flanks, we have thin crust, and maybe we are nearing a nemagmatic mode. Not completely, but we are tending to that. And so this is due to probably to this accumulated effect of transform fault and mantle. So in terms of synthesis and conclusions, I would say that first, large offset transform faults will have a significant role on the shaping of the oceanic lithosphere, because first they react to the kinematic chains they may deform, including forming complex multi-fault systems. They react to local stress and may deform significantly, and that's what we see with the origin of Atoba Ridge, which is linked to the increasing in length of the North March segment that it's propagating southwards and trying to enter the mantle domain, the transform domain there, and this induce local deformation. They are not barrier to mantle provinces. We see that the transition between a more fertile mantle in the north and the less fertile mantle in the south is actually inside the transform fault system, and that's not directly related to the transform faults themselves, or to the length of the offset. But they might be barriers to the flow, or at least they might be they are barriers to the propagation. Maybe if you have a strong age contrast, as we do have along transform A, which is about 20 million years age contrast, then we will have some resistance to the propagation of the ridge segment, and therefore the transform will have to deform. So there is some interplay in terms of the transform itself and the mantle. And second, both the transform cold effect and the mantle temperature and composition will have strong influence on the spreading process in terms of volcanism, contrasting with tectonics, and also in terms of ridge axis and stabilities. So we still have a lot to learn about these very large offsets and multi-fault systems. And especially, I think, the way they interact with the underlying mantle. We still have open questions about how these features do interact and how the mantle was going to have be important for the characteristics and the structure of the transform themselves. I think that this is, I leave with the references that I cited on this talk, and thank you very much. And sorry for being a little bit long. I had some issues with the PowerPoint. Sorry. Thank you.